Oh, I may not.
Thank you.
So I got your abstract, but I was curious, is this your lab? I have a no-name lab. Okay, that makes sense, because I was like, I have your abstract, but I don't have your lab. Okay.
Thank you. Sorry.
So, no worries. I still need to grade it then. I just wanted to make sure it's yours.
Yeah, me too. I'm on Zoom class. My teacher was like almost 6, so I just want to sleep. Yeah, possible for this. Yeah. Yeah. have two offers. I have
All right, yeah, so we have turning pile here. And then some of y'all have been on top of it, but otherwise, I'm going to remind you, don't forget those reading questions. So again, reading questions are online on Blackboard. All right. Let people kind of settle in. Any questions before we begin today? Questions? So yeah, just try to get labs and everything turned in as soon as possible, ideally a week after your lab. And then this is kind of a good catch-up week unintentionally. So if you've looked at the lab, we have what I like to call a paper lab this week. But please, so if you're sick or something, this would be the week to be sick, and then you could do lab at home. Because all it is like arranging these cards and kind of exploring what Mendeleev might have gone through. I still want y'all in class for this, but again, if you're sick, just check in with me so I know that you're doing the lab. I just don't want people disappearing. But if you missed last week, that means that this week is a good week to make up the lab. There's plenty of time, and then you can still take your paper cards home and do lab 3 at home. Again, worst case scenario. So good catch-up time. And then if you missed quizzes or anything, just again make those up ASAP there. Any other kind of questions, comments? Do we have questions over the material or anything? Any difficulties with balancing? Questions? All right, do we have questions over there? All right, so let's get started then. So again, ask questions, right? That's what I'm here for. And so otherwise, we're looking into chapter 4 now. And so again, the whole point of this class is to get a more sophisticated understanding of everything and essentially do kind of these back of the envelope quantum calculations and understanding periodic trends. So before we get into quantum mechanics or molecular orbital theory, we'll first go over again some of these trends. So you may have seen this in your previous chemistry classes. So we have our ionization energy. And so do we know what the ionization energy is? Yeah, but what we can summarize it. Yeah, it's up there, but what does it say? What does it mean too? So what's our ionization energy? And yeah, you can read it from the board.
The minimum energy needed to remove an electron from an atom.
And so let's look at that. So again, right, minimum energies. So what are we saying? So I would write an equation for this. Oops, I can't make space there. And so fundamentally, all we're saying is, okay, we have some sort of M, right, just our atom in the gaseous state. And again, these are gas phase calculations. And then we want to add some amount of energy, so usually abbreviated like so. And so we'll get into this, like I said, in this class. So this 1 here, meaning our first ionization energy. So removing 1 electron. And so with our first ionization energy, right, we just make an M plus 1 cation there, and then eject that electron. So a couple of things to note. So like we said, so this was in the gas phase, so that's important to kind of realize. And again, right, we're just looking at an atom, so we're not looking at it in a bonding scenario. It's just important to, again, put that context to it. And so then a couple of things about this process. So obviously it's an endothermic process. So we'll cover thermodynamics at the end of this semester, but that just means that it requires energy, right? So then we're asking, well, how much energy does it take to eject this electron? And so let's just focus first of all on the first ionization energy and its general trends. And so what can we say about first ionization energy? What maybe do you know, or what can we think about? What do we say about like the reactivity, for instance, of lithium, sodium, potassium, rubidium? And what does that have to do with ionization energy?
They have one valence electron.
So one valence electron, okay, so that's good. What else can we say about that? What about the increasing reactivity? What is
The valence electrons are further away from the nucleus.
So they're further away. So then what do we think about our ionization energy trend?
Requires lower the bigger, the further away it is.
Exactly. And so this is just our first ionization energy. And so again, just general trends, and we'll get into, or we're getting into it. So again, decreases as we go down, like you said, from those subsequent energy levels, right? So again, the effective nuclear charge is getting weaker as it's getting out there. Okay. Again, we're just thinking of first ionization energy. So what happens as we move across the periodic table? Again, for our first ionization energy. So it does increase, and then you're saying something of more valence electrons. Okay, so that's kind of getting to where we want to go with this. So now we want to answer, right, the why does it increase as we go across. Again, just general trends. So why would that be?
There's more protons too.
I mean, the protons, so the protons are always in the center, so that's true, but that's not really. And here's our trend. So this is just another way to show that, again, just kind of answering the why. We'll get into these oddities as well. But just what accounts for this general increase? So you had the right idea. We're like getting there. So we had valence electrons.
Does it have something to do with having more full electron orbitals?
Yep, exactly. So it goes back to effective nuclear charge. And so let's just kind of compare two for a thought experiment. So let's kind of fill in what's what here. So this just starts off, so hydrogen, helium, and then notice you're back at your alkali metal here, so lithium, and so then going across, so lithium, beryllium, boron, right, so just going across, so carbon, nitrogen, oxygen, and fluorine. All right, so let's start simply. So let's just compare for a second boron and fluorine. And so we should write the electron configuration. And again, we might want to go through, I'm going to make a new periodic table so we can put our electron configuration more clearly. I'm not trying to copy all this. So we're going to kind of keep doing electron configuration, and then we'll really cover it. But it all ties into our energy levels. All right, so we said we started off with our 1s, okay. Now this is our 2s. Boron starts 2p there. And again, we said our p is 1, 2, 3, 4, 5, 6 across. So our boron, our electron configuration is 1s2, 2s2, and then 2p1. And again, just pointing out some things, right? We can say then that boron has 3 valence electrons. Then moving over to fluorine, so again, we're still in the same row. And so filling in our electron configuration, so 1s2, 2s2, now 2p, so that'd be 1, 2, 3, 4, 5. And again, you can kind of write this general trend here, so NP5, again, going back to the reactivity. Okay, so there's our electron configuration, but now let's look at it in a slightly different manner. And so I'll reference P table. All right, so we look at P table. Again, this is just a reminder of our energy levels and how they fill up. That also tells us, again, how we fill it up on the periodic table, but it'll all come together. All right, so we're looking at fluorine. And so now we want to fill up, again, our p orbitals. So let's write it this way. So I'm only going to look at our valence electrons now. So 2p. So remember, there's 3p orbitals. I'll write it out for fluorine. So 2s, 2s. And then I'm just going to fill in the electrons, right, how they would fill up. So the s is lower in energy. So 2 in the s, 1 in the p for boron. Now fluorine, so 1, 2. Now 5 in the p. So 1, 2, 3, 4, 5. All right, so perfect. So just like he'd said, so we're still filling up our 2p. So as we go across, right? So now we're going across the periodic table. And so we're just filling up our same subsequent 2p orbitals, right? And so they're all the same distance. So again, our effective nuclear charge then is increasing, right, as we put more electrons in the same energy levels. So does that make sense for kind of the general trend? So now let's look at some little oddities here. So let's go back. And so there's a small exception to the rule. And you can see that's going from nitrogen to oxygen. And then that's repeated with phosphorus to sulfur for similar reasons. And then, of course, we'll talk about this or not really talk about this. But let's look at nitrogen and oxygen. So why do we have a weird discrepancy there, right? So why do we have kind of a break in the trend? We also have it in beryllium to boron, which let's start with there. And I think you guys can puzzle out what's going on in each of these scenarios. So now let's look at, so beryllium versus boron. And so again, give me the electron configuration of beryllium. So you can just shout it out. If you're in the chat, I'm always keeping an eye on the chat.
Isn't it 1s2 and 2s2?
So 1s2, 2s2, good. And then what about boron? So we just did it, so
1s2, 2s2, 2p1.
So 1s2, 2s2, 2p1. And so I can go ahead and draw out my energy levels, but before I even do that, do you kind of see why there might be a discrepancy in, again, our general trends and why boron actually has a slightly lower first ionization energy. So why would that be?
Because beryllium has, because the 2s orbital is full for beryllium, as for boron, the p orbital only has one electron.
Excellent. So did we all hear that, right? So that's a perfect explanation, and you could just add to that, you know, the S is, again, slightly lower in energy, so it's going to fill up with those 2 electrons. And then we have to think about the energy, so then it takes, right, some energy to eject that electron and break up that pair, so that's not that favorable compared to, again, ejecting that p electron. And then, right, this electron in the 2p is slightly further out, again, compared to the 2s, so you have some effective nuclear charge layer effects as well. And then, so we can look at that for nitrogen and oxygen. So again, let's repeat that process. So we'll look at our electron configuration. So nitrogen, 1s2, 2s2, 2p3. Again, looking at our valence electrons. So we have 5 valence electrons for nitrogen. And then oxygen, so 1s2, 2s2, 2p4 now. So let's see what's happening there. So oxygen, again, just to make sure we're all on the same page. So 6 valence electrons. And again, right, things should hopefully start to feel a little almost like repetitive, and that things are reinforcing one another in different manners, right? So again, 6 valence electrons. We're 2 away from our octet. So again, we know it's going to be a -2 there. So all these things are kind of in your head. All right, so now let's draw out our simplified orbitals, atomic orbitals here. So 2p, 2s, and again 2p, 2s. So I'm just filling in our electrons. So nitrogen, 1, 2, 3 versus oxygen, so 1, 2, 3, 4. So what do we notice about this? And so why might oxygen be lower in energy? What's just the difference between them? Yeah. Well, so shielding comes into play when we add like extra orbitals, right? So we don't have extra shielding from here to here. But what's happening? And again, right, let's look at what's, so we expect oxygen to be higher in our first ionization energy, but it's actually slightly lower. So why is that? And again, what's the main difference between them, looking at it?
Because it needs 2 electrons to create a perfect valence.
Well, that's a different set of information, right? So yes, we can see that it's missing 2 electrons here, so that's where the octet rule comes into play. But we're not, and so that gets into other things too, right? So of course it wants to gain electrons, so already it's going to have a high ionization energy. But there's still something that we're missing, right? Because again, we're just comparing nitrogen and oxygen. So it doesn't quite have to do with the missing 2. But what else is different between them? Just like looking at the pictures too. Shouldn't be 2. I'm not trying to trick y'all, right? Like, just look at these 2 diagrams. What's different?
I don't know if I'll say it right.
Yeah.
Obviously, there's 1 less electron on the nitrogen and 1 on the p orbitals. Am I saying that right?
Yeah, but then what does that mean that there's 1 less electron? Okay, yes, that's true. So then what happened to the other extra electron? so we had to pair it, right? So in the nitrogen, they all got their separate orbital, right? So they're all in one separate p orbital. But okay, we got over to oxygen.
So is it because of the electrostatic repulsion between the two electrons?
Yep. So basically, you pay, I call it that you pay an energy price, right? And this is also, I don't know if you talked about the Hund's rule, like the candy rule in high school. So the oversimplification of the Hund's rule is like, okay, every orbital gets an electron, right? And so it's kind of more clear when you look at it this way. And well, why is that the case, right? Well, it has to do with, again, energy, right? So, okay, they're all degenerate, so that just means they're all the same energy level. So right now, it is favorable, right, to stick one in each separate orbital. But then, yes, once you try to go to pair it, excuse me, then there's some repulsion, right, from your two electrons, and then obviously they have to be opposite spins. So that's why I draw it like so. I don't know if I made that clear, by the way. So I should make an aside. So, right, the electrons. And this is getting into quantum numbers, which, like I said, we're building to. But electrons formally have either a +1/2 or a -1/2 spin. And so I just show that by drawing these up-down arrows. And so you can't have an electron occupying the same space, so we can't have like that sort of thing. So that violates quantum mechanics. So that's why I have the up-down spin. But yeah, we still pay a price. And so basically then we're saying, right, it's kind of favorable to eject that electron, right? Because now we're back to this scenario where every electron is in its own happy orbital. And so again, that's why we see that trend. So, okay, oxygen then is slightly less because we did pay that energy price for pairing. So that is again reflected there. And then, of course, back to increasing with our general trends of fluorine there. So that was good. So, right, again, we're just trying to really dive into the atom structure and kind of get past any oversimplified views. So that's excellent there. And then, of course, trend repeats, like we were saying. The ionization energy of our alkali metals decreases, again, as we go down. That reflects the reactivity. So, again, everything is just coming together, hopefully. All right, so now let's look at the subsequent ionization energies and what that means. And we have our ionization energies, and so basically all we're saying is, right, we can continue really until we eject all the electrons, right, from an atom. That's what we're getting at. And so we can start then just going at our second ionization energy. That means that we're starting with our cation, and again, we're still in the gas phase for these calculations, and then we would call ionization energy 2. And then now we have our 2+ cation, still just ejecting one electron. And then, of course, right, we can continue, so I'll just go one more. So third ionization energy, and now we start with metal 2+, and then add again the correct amount of energy, resulting in our 3+ metal cation, and then again one electron at each one of those steps. Let's see what, so blah, blah, blah. All right, so then, right, our successive ionization energies, basically it depends, right, on our valence electrons. So what we want to notice is what I call like the jump, right? So that's kind of the whole point in a lot of these graphs. So looking at what's shown here, so right, we have sodium's ionization energies, so it's just graphs, so right, first, second, third. And so what you're supposed to notice is where does this large kind of jump occur? And judging from this graph, right, you're supposed to see that there's a large jump here. So you go from 496 to 4,000. And so this is telling you, right, that we're going from our valence then to our core electrons. So in my mind, that's the main use of the ionization energies, or the subsequent ionization energies, is you're given this table of data, and then you're trying to figure out, well, how many valence electrons does that have, or likely have, again, based off of this data. And so magnesium, right, we're looking at it, so we have these first two values are pretty close, and then this third one is quite large. So again, we have a large jump from our second to our third, and so that's telling us, right, that we would then have 2 valence electrons, since the jump is when you go to the third one. And so again, that's telling you that this third one is getting into our core electrons. Does that kind of make sense? And so your book has this table, right, and it just kind of goes through these successive ionization energies. And again, they're just showing us, okay, so we're going right across our third row on our periodic table. So, okay, sodium, magnesium, aluminum, silicon, phosphorus, right? So that's just our third row here. And again, we're just seeing where the jump is, and they put a nice stair-step graph to kind of help us. And okay, again, sodium, right? We make this huge jump from our first to our second. So again, you know this now, or you're learning it. You have your periodic table to help you. But right, we know that sodium, again, alkali metal, 1 valence electron, matches with the data there. So again, magnesium, right? You have a large jump here corresponding to 2 valence electrons. Then aluminum, right? Again, you can kind of see, okay, these 3 are clustered together, large jump from here to here. And again, we know aluminum has 3 valence electrons. So then that is just repeated, right? So silicon, 4 valence electrons, phosphorus, 5, sulfur, 6, and then 7. Of course, we're kind of missing data. And then you can see for argon, right, starts off high. And then something else to note is just each subsequent ionization energy is increasing, right? So that holds true for all of them. So like looking at magnesium, we have our first and our second ionization energies. So again, just kind of thinking about the energetics involved in forming ionic compounds there. And we'll eventually kind of break down the energetics of, like I said, forming an ionic compound as we progress. All right, does that kind of make sense? So you'll probably be like given data on an exam. So usually what I do is I have some like values, and then you have to guess like what element might it be in, or how many valence electrons, something like that. So I usually ask, like how many valence electrons. All right, so now we want to get into writing these Lewis dot figures. But again, we want to make sure that we kind of translate it correctly. And so what I mean by that is, again, we're taking a more sophisticated approach than high school chemistry potentially. And so the way I like to think about it and kind of simplify these Lewis dot structures is we can go back to the energy levels, right? So usually we use our Lewis dot structures to represent our valence electrons. And so the easiest way to translate it in my mind is we can take our electron configuration here and think about writing it like so in this representation. And then we have 1, 2, 3, 4 orbitals, right, that we care about the most for valence electrons. And we have kind of 4 sides of a square. And so I'm just going to rewrite, again, how I would go about figuring this out. And so just starting, I'm just looking at, again, because now things are going to repeat on a pattern. So group 5. Again, kind of looking at nitrogen. So I'm just kind of copying over what we had established. Okay, it fills in its electrons like so. And we can write our Lewis dot figure. Again, we have 1, 2, 3, 4 sides. It doesn't matter what side you want to call S and which side you want to call P, right? Your atoms rotate around in 3D anyways, so orientation doesn't matter. So I'll just put 2 dots on one side. So that's, again, like I'm filling in my S orbital. And then my 1, 2, 3 dots. So 1 for every P orbital, right? So I'm not going to pair them until I have to. And again, just write that. Try not to move too fast. And so I'll, again, repeat the process for oxygen since we looked at it. So group 6, looking at kind of representative of oxygen. And we did have a paired electron. And again, doesn't matter what side. And so this is pretty powerful too. So we're already starting to get a lot of good data. So don't underestimate the power of, again, cartoon representation in chemistry. But for example, we can start teasing out bits of information. For example, right, like nitrogen typically forms 3 bonds, and you can see that, right? It has 1, 2, 3 little electrons ready for bonding. And so that's typical of group 3. And again, this is kind of jumping ahead, but I just want you to appreciate all the information that's packed in here, right? So then we're learning, okay, well then I'll probably form some sort of compound like that, like ammonia, so we can, again, figure out how that happens. We'll revisit this in more detail. Again, I'm just trying to get you to see, like, everything's connected. We're getting a lot of information from this. Again, right, oxygen. Boom, we know that this typically makes 2 bonds. And we probably know that from water, but again, we'll keep kind of investigating that and how these lone pairs, I'm drawing it appropriately, but again, right now we haven't covered it, but we'll get into the geometry formally. But right now we're just taking information in our Lewis dot structures.
Can you show us the Lewis dot structure for sulfur?
Yeah, so sulfur should be the same, right, as oxygen. Do they have it on here? So I would agree with this statement here. Again, they just chose to put 2 dots on opposite sides. It doesn't matter how you write it. I would probably write it more like oxygen and think of its sulfur dihydride compounds, right? So that's typical geometry. And so yeah, you feel free to put the dots anywhere. So kind of looking, right, again, we can establish general trends. So obviously our group 1 alkali metals should all just have a dot somewhere. Again, I'm not picky where you put your dot, but just signifying, again, our NS1 electron configuration. So just building upon that, what we've been saying. And then helium, so I like this. I like your book. So I don't always agree with every source. For example, right, you can certainly find sources on the internet that will write a Lewis dot structure like that. But to me, that doesn't mean much because, again, right, what are you trying to represent? I'd rather represent that, again, we are filling up our 1s2 then orbital here, right? So obviously helium fulfilled by the duet rule. And then lithium, so beryllium, again, that's fine. So boron, I would say you could start to see discrepancies here, kind of based upon, again, what you want to show. So let me just sketch. So group 2, again, group 2 is pretty self-explanatory. Just keep those dots together. So again, we're representing NS2. But like I mentioned, so group 3, you might see, I'll put boron aluminum, you might see some exceptions. So again, it depends kind of what you're trying to highlight, right? If you're trying to emphasize this NS2 and P1 structure, you may, again, see that representation. I'm fine with that. But other people want to emphasize that boron and aluminum does this too. They make covalent compounds that are hybridized in this manner. So 3 bonds, trigonal planar, again, we'll get there. So this would also be okay. So I'll say okay as well. Shows hybridization and bonding. So on a test, I would accept both of those. And then, so let's look at group 4. So I'm okay with this silicon representation. I don't know about this carbon one. So again, it depends what we're trying to show. So let's look at group 4. So group 4, again, is typically going to be NS2, NP2, right? But we have carbon as kind of the exception and is usually presented as such. So again, most people like to emphasize that carbon likes to make 4 bonds, and I think we kind of touched on this, right, as to why we're carbon-based, but it likes to also double and triple bond with itself and do all sorts of things. So usually its Lewis dot structure is shown like this. Again, this emphasizes the fact that it wants to make 4 bonds, and again, also the tendency of carbon to hybridize, which we'll get into what this means. Again, we're still building. So this is fine for carbon, but then I would say that silicon and germanium should both be drawn like this, and tin as well, with 2 dots on one side and 1 dot on each side. And so why I would say this is because, yes, we do have experimental evidence for this. And so while you can isolate a carbene as a divalent species, it doesn't really exist that well. So actually these carbenes have to be stabilized. But silenes and germalenes, those are more readily available. You can actually buy germanium adducts as dicoordinate. So yes, there's evidence for this sort of reactivity versus the difference in reactivity of carbon. So that's what I would put for that electron configuration. And then we're back to group 5. So we saw group 5 again, right, with our 3 bonds. That's all coming down the pipe. So there it is as well. I like that representation. Group 6. So again, that's fine. And then halogens, group 7. So again, they're just effectively missing an electron at that point. And goes back to the reactivity. So NS2, NP5. And properly, right, you should fill it in. So 1, 2, 3, 4, 5. So following what I'll call our Hund's rule, our candy rule, but again, just thinking back to filling in our degenerate p orbitals. And that indicates, right, that our halogens tend to make 1 bond. Again, typically, right, you can see other crazy hypervalent or extended octet scenarios, but we'll get into that later in the course. And again, right, they're 1 away, so that also speaks to its oxidation state of -1. And then so group 8, obviously, so our noble gases, and I'll kind of leave helium out of it, but then the rest, like neon, for instance, I would just fill in, right, with all 8 electrons. Same thing. So that's the other thing, right? So krypton, again, I would just kind of simplify it with 8. And so that's the other thing. So like, let's say we're looking at selenium or bromine over here. You generally don't count the d orbitals as part of like their valence electrons. It's only if we're talking about one of these transition metals that then we start looking at, again, how many d valence electrons. But we'll save this for third quarter. So that's, again, we'll save all the transition metal fun for later. But yeah, again, I would just treat these as 3, 4, 5, 6, 7, 8 valence electrons respectively. All right, questions so far on writing our Lewis dot structures? Do we feel okay about that? And again, it should just be kind of a repeating pattern, but this is again where we see trends and reactivity, so it's driving all of that. All right, so then we start getting into kind of quantum mechanics, right? And the history of quantum mechanics. I had found a good article that I was going to share if I didn't lose it.
Is it in German?
It was not in German this time. Thank goodness. This was from Physics, this physics journal. I should probably post it. But it's just kind of cool, and it's a good appreciation, right, of just kind of everything was done in pieces. So I'll probably post that. And so basically that's kind of where we start off with in the book, is we have a bunch of smart people, right, all kind of attempting to, well, ultimately create this field of quantum mechanics, and right, this eventually gives rise to computational chemistry, which is super powerful and necessary today. But again, I don't even know if they really understood like how amazing and fundamental some of their work and observations were. And so, okay, right, we're just kind of orienting ourselves in history, and they're still trying to figure out, right, kind of what the electron is ultimately. Like, yes, they have discovered it. Yes, they know there's a bunch of like little electrons, but then, right, still trying to understand it. And so just defining what quantum mechanics is, and again, we'll kind of get in as we get into this chapter. So it's dealing with extremely small pieces of matter, such as, right, the electron, and they behave much differently than matter of the macroscopic world. So we'll kind of answer, again, why that is. And so we have to understand that, right, these particles behave strangely. And again, we'll get into what experiments led to this. But part of the problem, and where they landed at, is that these subatomic particles didn't behave like you might expect it to, right? And so the saying is this wave matter, wave particle duality. But essentially, right, you expect the electron to maybe behave like we would with macroscopic. You know, you throw a ball, you expect it to just go in a straight line trajectory. But again, obviously that didn't happen. So let's keep going. And so part of the problem is, of course, right, it's incredibly difficult to both observe it and then it gets perturbed incredibly easily. So again, right, if we're just trying to study the electron, then, well, electrons are obviously incredibly small, right? So how do you even observe it? So that's the first question. And then the other issue, so, right, as you try to observe the electron, well, it's so small that once you observe it, right, then you start to perturb it and change it and alter it. So, right, even shining a light on the electron can alter its course. So again, how do we study it? And then ultimately, right, what we're getting at, though, is all of our behavior of our atoms, though, is dictated, right, by the electron and all these things of orbitals. So blah, blah, blah. So, right, it tells us basically everything. And so, again, this gives rise to kind of quantum mechanics. And the other kind of key piece is, right, the electron is not just a little piece going around, but we want to change our view as just, right, probable positions. So, right, when we talk about the cloud, we're just looking at really a probability density map, right? We're saying that the electron is most likely here. If we could, again, magically stop it, observe it, right, we could find that it would most likely be in this center. And again, we're getting to that.
So, does it actually exist in that probability state, or is that just an effect from the fact that we can't directly observe it without altering its course?
So it exists, right, in these orbitals. So I think we have evidence for all those and like the shapes that they take. So yeah, it is, right, because ultimately it goes from solving the Heisenberg, or attempting to solve the Heisenberg equation, right? So you can't solve it for anything, but you can kind of estimate it. And so that's, again, what quantum mechanics is trying to do, and put all these things together. And, right, again, we're already kind of getting there, right? We're looking at the trends. So all that is, again, going back to those energy levels and, again, our more sophisticated understanding of that. And so we kind of are getting to this, right? So why things are certain properties, why things form anions or cations, right? Why things are reactive. So we're answering all of this, right? Again, we're just kind of taking a deeper picture. Sorry. Just trying to remember where we were in history. All right, so light, and let's kind of look at the history of this, right? So going back to our history article. And so, of course, light is a form of electromagnetic radiation. And so that's how it kind of started. Is you had, I believe it was Planck, right? And he was trying to figure out this black body emission, right? So again, studying this electromagnetic radiation. And so he was looking at this black body emission spectrum at a certain wavelength. And, right, he noticed some observations that when this black body object is heated, right, it glows red at first, then becomes white, and then has more colors. And so what's kind of funny is, again, Planck didn't really fully understand what he was observing. And so he just kind of came up with these mathematical equations and kind of figured out, again, kind of by accident, that it's quantized. So let's keep looking at that. Well, before we dive again back into quantum mechanics, well, let's just look at light. So like we were saying, right, light is a form of electromagnetic radiation. And so looking at it, right, we have our two different components. So we have, right, our perpendicular oscillating waves. So one of them being an electrical field component, and then the other magnetic. And so, of course, the other kind of key is that all electromagnetic waves move through space at a constant speed. And so this is often, right, a constant, the speed of light, so 3 times 10 to the 8 meters per second. So I'd probably write that down just because it's pretty important.
I thought there were slight variations when it moves through material.
Yeah, but that's why we're space.
Oh.
Yeah. And so then how do we characterize these waves? So we have our amplitude, and so that's defined as our height of the wave. So from either our base to our height there, or to our trough. And then we can measure our wavelength then. So our wavelength goes from peak to peak. And so again, amplitude, I forgot to say that that gives us a light intensity. And again, we're just saying that we're ejecting more photons, right? So we're not changing the energy, and we'll look at that. And then again, our wavelength, like I said, it's measured from crest to crest or trough to trough. And so now looking at these properties, and again, this may or may not be obvious to us, but wavelength and amplitude are independent properties. And so different wavelengths result in different colors. Obviously, right, this is only referring to the visible part of the electromagnetic spectrum. Oh, you would think that I would have a graph. There we go. So right, there's our full electromagnetic spectrum. So obviously, the visible region is a small portion, but then you have, right, radio waves, microwaves. So obviously radio are the longest, and they tend to travel further, again, if they're longer. So like AM waves travel pretty far. And then go to microwave, infrared, visible, and then ultraviolet, and then obviously higher energy, so X-ray and gamma. And of course, these can all be DNA damaging. Right, going back. All right, so wavelength, again, determines what kind of wave or color. And then amplitude is just dependent on intensity. So different amplitudes, different brightness. So right, same wavelength though, so this could be a red light. And so our color then is again determined by our wavelength. And so this is kind of, we're getting into it. So that determines like what color everything is. And why everything is white though, like most organic compounds have their transitions in the UV range, so that's why everything looks like white to us for most like organic compounds. And then of course the fun transition metals, why they're fun, colorful, is because they tend to have more transitions in the visible region, and same thing with like their flame test, you can see that reflected. And then white light is a mixture of all the colors of the visible spectrum, and so often abbreviated Roy G. Biv, in case you've never heard that, just so we're all on the same page. All right, I think that'd be a good, let's take a break before we start getting into the math of it. So we'll come back. And so like I said, we'll just continue with kind of the math of our wavelength. So take a 10-minute break, so like be back around 12:05-ish. And I'll also attempt to hand back more stuff. All right, do we all make it back from break? All right, so now we're just kind of going over again, right, how to characterize our wave. And so again, other ways to describe it. So we have what's called frequency, or this little mu or v, this funky V shape, right? Not to be confused with velocity. But this is frequency, so this is a number of waves that pass a point in a given period, right? So again, if you're thinking about this wave, right, maybe you want to look at every time a crest goes by, right? So that is your frequency. That's what that's telling you. And so the unit for this is hertz, or it's just inverse seconds. And so again, 1 hertz is an inverse second, so don't let those units confuse you. And so energy, we'll come back to this and discuss other relationships, but it's proportional to, right, the amplitude of our waves. The larger the amplitude, the more force, and so usually that's how many photons, and then the more frequently they strike, the more total force. So then we have, again, how to characterize our wave. So I would star this, write this down. So this is, right, your equation that you're going to be using. So our frequency is related to the speed of light, so 10 times 8 meters per second, divided by wavelength. And so I think the hardest part of this chapter is just remembering to put your wavelength in meters. So you want this in meters, right, to match our unit of our speed of light, right? So our speed of light is in meters per second, so our wavelength should always be in meters. And so other things to kind of note then with this relationship is we have a long wavelength that gives us a low frequency. And again, that kind of makes sense if we go back to our chart. Where'd my chart go? There it is. Right, so again, long wavelength and low frequency, and that makes sense, right? So it's going to take a lot longer for that point to come by if it's a long wavelength. And so I like this graph. Again, we can just kind of put it in context. So if you see something 10 to the 4th frequency roughly, right, that's going to be pretty low or large wavelength. So radio waves, again, kind of see that. And we'll put this again all together mathematically. And then again, short wavelength, higher frequency. So I would again think of our gamma rays. So they're high energy, so high frequency, right? So they're going to be really small. You kind of think about it too, right? Their wavelength. So obviously, if we're looking at our crest, the crest is passing through whatever measured point pretty rapidly, again, compared to these long radio waves. And again, the speed of light is constant, so obviously we'll use this. And so if we know the wavelength, we can find the frequency and vice versa. All right, so let's practice that. And you'll have to practice your converting a little. So it wants a wavelength in nanometers of the red light emitted by a barcode scanner that has a frequency of 4.62 times 10 to the 14th hertz, or inverse seconds. And so you can plug that in. So I'll let you plug that in. So what should we do mathematically? So we're trying to solve for wavelength. So what do we need to do? So if you're lost, right, there's a few different ways to figure it out. You have, I always like this triangle trick, right? So you can set this up and cover up whatever we're trying to solve. So, okay, we're trying to solve wavelength, so cover that up. And that's telling us to do the speed of light divided by our frequency. And so if we set that up mathematically, it should also work out with our dimensional analysis. So 3 times 10 to the 8, again, meters per second, setting up our dimensional analysis. And then, right, this is given, so this is hertz. So you can just think about it as 4.62 times 10 to the 14, right, inverse seconds, so it's just a relationship. So now I'm going to write seconds on top. That puts this 4.62 on bottom, right? And again, that's what we said, just kind of without the dimensional analysis. So my seconds cancel, and we're going to get units of meters. So let me plug that into my calculator. And so make sure you're using this little second E button, again, to measure the exponent. Otherwise, right, if you punch in times 10, then you'll do some order of operation thing wrong. So just use the E button. And so then I get something like this when, right, it's punched into the calculator. So 6.49 times 10 to the negative 7, that's in meters. But then it asks for it in nanometers. So I'm just going to do a quick conversion. So 6.49 times 10 to the negative 7 meters. And then, so I'll try to hand back the quizzes. I'm just slow and I still don't know all of you. But that's my only criticism of the quizzes. They were pretty good, but if people did make errors, it's usually because they didn't write out, you know, their conversion factors properly. And so make sure we're wanting to go to nanometers. So I'm going to use, there's 1 times 10 to the 9th nanometers and 1 meter, right? So make sure whenever you're writing any conversion factor, make sure you have, right, many small units in the big unit or so forth. Some people did some accidental like swapping of their conversion factors. But then what should we get for our final answer? Yep, so 649 nanometers, so I'm sticking with the 3 sig figs there. So yeah, 649 there. Questions on that one? It's not too bad. So again, just watch units and conversion factors. So here's our, again, our picture of our electromagnetic spectrum. So I would just, again, kind of familiarize yourself with it. You can always remember to, right, again, you have your Roy, I didn't do that very well, did I? Roy G. Biv here. And so you can always remember, right, that red is our longer wavelength, right, and it's closer to infrared. And so lowest energy, right, is red over here. So lowest energy, comparatively speaking. And then obviously, right, we have increasing energy as we go through the colors, and then violet is the most energetic of the visible light. So most energy, and then obviously, right, highest frequency, smaller wavelength, we can also say. So just kind of, again, keep those things in mind. And then violet is next to ultraviolet. So again, right, higher in energy, so that's why violet is on that side. And so again, just recapping that our visible light is a very small fraction of the electromagnetic spectrum. And then we mentioned, so radio waves, again, have the lowest energy, and they can travel, again, quite long distances. Obviously, eventually, right, all these radio waves get absorbed by everything, right, air, buildings, blah, blah, blah. So that affects how far it travels. Gamma has, again, the highest energy, and that's going to be, like I mentioned, pretty DNA destroying. That's also what I should post, is like there's some book out there that like goes through this horror story of it was in Japan where these two people were exposed to like very high amounts of radiation, and it's basically looking at like the process of them dying because their cells are so DNA damaged, so that like the cells literally can't repair themselves. So yeah, like the skin starts falling off and all sorts of crazy things, and no bone marrow. Anyways, all that to say is, again, DNA damaging with that high energy. And so obviously, right, UV rays can also potentially be damaging. So obviously not as quickly destructive like a gamma ray, but, you know, over time those UV rays could potentially alter your DNA. They also can, you know, break down plastics potentially. So all sorts of things to think about are UV activated experiments. And then, so next lab we'll have some fun. So this is my warning too. So next week, wear your pants. I just don't want anybody spilling 6 molar HCl on themselves. And so we're going to, again, kind of do some fireworks in the lab. And so basically what's happening with the fireworks is there's a bunch of fun metals and magnesium in there. And then, right, kablooey, lots of explosive energy. And with that heating up, right, you get all the light release. And so actually what's happening, where are we? Blah, blah, blah. There we go. This is what I'm looking for. So anytime that you add energy, so either right by heating or electricity, you're promoting some electron, right? And so let's just say it's starting, so it's indicating that this is our valence electron, and then, right, you add energy to it, so it gets promoted to a higher energy level. And right now we've just taken, again, a simplified Bohr approach for a second so that we can look at it simply. But it gets elevated to one of these higher energy levels, and then it relaxes back down. And once that electron relaxes back down, that energy, right, that it gained gets released as light. Again, I can't draw, so light, yay, happy colors, yay, right, everybody likes colors. And so that's, again, what gives you the colors of pretty fireworks and all those sorts of things. Or the other thing that you often see these in now is like those campfire salts. Have you seen those things, right? No? Yeah, yeah. See, some people know what I'm talking about, like where you turn your campfire green or whatever crazy stuff. Yeah, most of it's just like copper salts, but that's all it is. And so same thing with neon lights, although now it's like harder and harder to find true neon lights. They're all replaced by LEDs, but anyways, we do have wonderful lamps in lab. So like I mentioned, we'll get to see that and see the pretty colors, right, as electricity is passed through that gas. Again, electrons being promoted, relaxing back down, and yay, pretty colors. And so then, right, well, kind of, what's the point of the pretty colors other than, right, people like pretty colors? Well, how do we figure out, again, what the stars are made of or anything, right, our whole galaxy? Well, we have this light, and then we can separate this light, right? So all this prism does is separate our light into particular wavelengths. And so this either gives us our emission spectrum if we're looking at the light released, or if it's measuring the absorbed light, it could be an absorption spectrum. And so what the key part of this is that each element has its own unique line spectra. And where do I have? Somewhere I have a link. Well, I'll find it. Because somewhere I have a link to a bunch of emission spectrum. Oh well, I'll find it later. But we do have nice posters in lab that also show this. Like I said, we won't bust them out until next week, but we have this whole periodic table, and it shows, again, every element's unique line spectra. And so now we'll look at hydrogen. So obviously hydrogen is going to be the simplest since it only has, again, one electron. But it's already fairly complicated, at least for having one electron. So again, you'll do this for yourselves, but you'll have your hydrogen lamp or other lamp source in lab, and you'll do essentially the same thing. So we have these little spectrophotometer prism things, essentially, where you do this, that does this, right? So you put your spectrophotometer up, so there's a slit in your little device as well. So you line up the light, and then what it does is same thing, separates the light, and then you'll see it, again, you'll see it in lab. But then what you're measuring, right, is you're seeing all these different unique pattern lines. And so hydrogen, I think it kind of has more than 4 distinct lines. And then these are kind of other elements. So helium, again, is pretty simple. So 1, 2, 3, 4, 5, 6 lines shown here. And then barium. And then obviously increasing in complexity. And then this is just showing you what a continuous white light spectrum looks like. So obviously the entire rainbow. And then these are more like absorption spectrums where they kind of get blanked out what's being absorbed, so they're kind of highlighted. So it just depends, again, what you're seeing versus your emission, where you're just seeing the colors pretty clearly. And so this is kind of how, again, we got to these quantized ideas. And so again, kind of going back in history, and I think we kind of mentioned this, where, right, we had our Rutherford model. And so what did Rutherford find again? Do we remember? So he found the nucleus, right? So he established that there was a nucleus. And so all we have is like, okay, we have a center, and then, right, our electrons are in some sort of amorphous cloud. But that doesn't really explain all these things. And that's how Bohr, again, came into play then. So I think Bohr was looking at some of this absorption spectrum and, right, again, saw this for hydrogen and then used it to speculate. So that's where he came up where this energy was quantized, since again it's certain wavelengths. And right, so again it has to be specific amounts of energy. And so that's again kind of where we get our Bohr model. And this is a pretty good, again, simplification of it, right? And I think I kind of mentioned it before, how we can still use this Bohr model for our principal quantum energy levels, right? But then we're kind of diving in deeper, since some of these may have p orbitals, or we'll get into d orbitals, f orbitals, theoretically g, but again, well, I'll get too excited and start jumping all over the place. But essentially, yes, so that's where they started kind of coming up with this idea that it has to be, right, a particular jump with a particular energy level that corresponds, right, to a particular color. And so that's, again, what gets eventually teased out by researchers over time. And we'll kind of see this again as we kind of go through the course. But you can pair up, right, a lot of these transitions, even when you go on to the transition metals and you get complicated D transitions, right, that still correspond to colors. Well, there are scientists, right, that piece out, again, what transitions they belong to. And so just kind of, again, we're looking at just a rough sense right now. But we can first appreciate, so we have this small level transition, right, going from our 3 to our 2 energy level. And so that results in a red color. And again, just thinking back, red is a little lower in energy from our visible spectrum. And then looking at these higher jumps, like from 4 to 2 or 5 to 2. So again, those result in higher energies. And again, you see that reflected in our wavelength. And so, right, that's the key, that this transition, so each transition corresponds to our particular wavelength, right? So then, again, even though we just have one electron for hydrogen, right, it's just where it's being promoted. So we can have, obviously, right, you have a whole bunch of hydrogen atoms and electrons when you have a gaseous sample. So then some of them are being promoted, right, to higher energy levels, resulting in the violet, blue spectrum, and other are doing lower transitions, right? And so they're all just going all over the place. And again, gives us kind of our unique fingerprint. All right, so then we'll start looking into the math and what calculations we're going to be doing in this chapter. And so energies are defined as being negative, and so that means an electron's energy is lowered, aka made more negative, as a result of its interaction with the nucleus. And then we can define our energy of 0 when we have an escape from the atom. And so as n gets larger, the following occurs. So the amount of energy between orbitals gets smaller, and the energy of the orbital becomes greater. And again, right, we're not really saying anything new. I would just recorrelate it back to here, right? So we're saying the largest transition is from our 1s to the 2s, right? And often I'll try to kind of reflect that. So 1s, right, 2s, and then 2p, but then they start to get a little closer. So that's all we're saying there. So right, 2p, and then notice how that 3s, and there's a better diagram for this. So this is another good one. Again, this is kind of oversimplified with our Bohr model, but again, we see that, right? So our n equals infinity, so we reach kind of our limit here. Again, each subsequent energy level will be extremely close. biggest gap, right, from our 1 to 2. So again, just kind of appreciate those things. And then, yes, we have other hydrogen transitions that are not in the visible range, right? So we have some UV transitions over here. Obviously, our 4 main kind of visible ones. Then we're going to have some lower energy, right, IR ones. And then formally ionization is defined as, right, going from our n equals 1 to then infinity, right? Then we've ejected it, and that would be formally ionization. All right, so then we're kind of, again, jumping around in history. So let's get into kind of Einstein. And so kind of back to our history article, right? So Planck had kind of come up with this idea. And again, like I mentioned, he just kind of theorized it, right? He did the math kind of checked out. He's like, I think this is quantize the energy. And so then, okay, Einstein wanted to take this a step further. And so this is what's going on here. And so from, right, our kind of understanding, or at least at this time, their understanding of what should have happened is like, okay, let's take this light source, and let's just say he started with a red light source, right? And so their thought was, okay, what if we shine a really, really, really bright red light at this metal? Will it ever eject any electrons? And so he did that, and shining this light, right, the red light, nothing happened, okay? But then, once he chose another wavelength, right, so now shining a different wavelength, not necessarily at a stronger power, it ejected the electrons then. And so, right, this is giving us, again, more evidence that it's quantized. And so again, right, going back to kind of what should have happened, or again from our classical explanation. And so again, according to kind of classical wave theory, we assume that, right, if we kind of shine a brighter light, more electrons should be ejected. But again, what he found is if he was not at the proper wavelength, right, no electrons were ejected. And so again, they expected that if you have a dim light, that there should be a lag time. But that was not the case, right? Again, it just had to do with the frequency. And so then, right, this again kind of goes back to how things are quantized. And now we kind of go with this, well, we need some minimum frequency, right? We're trying to achieve the correct corresponding energy for, again, whatever transition we're trying to accomplish. And so that's what that proved. So again, we have to have the correct frequency. So again, from my example, right, red light is not going to do it. We have to hit whatever blue light, green light frequency. And then the other key point is our high frequency light from a dim source cause electron emission without lag time. So again, right, once you switch to the blue light, even though it's dim, boom, electrons are being ejected because, again, it's the appropriate frequency, which goes back to our energy of our particular wavelength and color. So that was pretty exciting at the time. And so again, now we're just kind of putting Planck's theory together with this photoelectron effect. And so again, just kind of building, so right, we're kind of just seeing all the pieces too of quantum theory. That, okay, well now we start getting into the idea of photons and the idea, right, that light is little packets of energy that again has to have this kind of minimum threshold. And so then we also come up with that the energy of a photon of light is, again, proportional to frequency. So I would probably write that equation down. And so notice, these are just kind of manipulations. So, right, we substituted in for our frequency here, and so that gives us this equation where, again, energy is proportional, and that's Planck's constant times the speed of light over the wavelength. And so Planck's constant is here. So 6.626 times 10 to the negative 34 joule seconds. And again, speed of light. So 3 times 10 to the 8 meters per second.
What was the
Oh,
value for
sorry.
10 to the negative?
And so now we've kind of made it almost full circle here, I would say, right? Because now we've kind of gone back to, well, why does it matter? What does this quantum behavior kind of mean? And so de Broglie was the one that kind of theorized this, right? He was saying that really all particles have some sort of wave-like character, and we can calculate, right, our own wavelength in a second. And again, we'll see kind of why it's relevant or not. And so he predicted that our wavelength of our particle was inversely proportional to our momentum. And because, right, our electron is so small, and we find that it has, right, this same wave-like behavior. And so that's why, again, the quantum mechanics applies, and we start to get, right, those strange observations. And so now we're back full circle. And so this calculation is for the de Broglie wavelength. And so your de Broglie wavelength is equal to Planck's constant divided by mass times velocity. And so let's run that comparison again, right? Like, why do we not exhibit strange quantum mechanic behavior while, you know, electrons and photons do? So let's calculate the de Broglie wavelength, and let's do for a 70 kilogram person going at 1 meter per second, and our mass, again, is in kilograms in this formula, because we're in physics world. And then let's calculate it for an electron, and I'll give you the mass of the electron, so 9.109 times 10, it's the negative 31 kilograms. And let's just say it's moving just under the speed of light, speed of light at 5.6 times 10 to the 6 meters per second. So go ahead, maybe try the person first, and then I'll kind of check in with you all, make sure the calculations are going okay. Otherwise, just continue on to the electron so that we can compare them. All right, so I'll just sketch out the person one so you can kind of see where you're at. So does that look all right for the person? And then I'll go ahead and plug in the electron. So again, let me know if you have questions about this or got a different number. So I'm just plugging in the mass. Of course, our velocity. So just watch order of operations on this one, of course. So I'll multiply the bottom first, and then I'll divide just so I don't do any screw-ups. Oops. Then I get 1.29 times 10 to the negative 10 meters. And so what do we notice about these? And again, how does our wavelength compare to our size, right? So 9.46 times 10 to the negative 36 meters. So pretty small, right? Like ridiculously small, and then most of us are like roughly a meter in height, right? Plus or minus. So again, that's why our de Broglie wavelength is not of relevance, right? Because it's so tiny compared to our size. But for the electron, it is relevant, right? So its de Broglie wavelength is 1.29 times 10 to the negative 10 meters. And the electron is roughly going around the atom that's about this size, right? So that is why it is relevant for our electron, right? Since they're on about the same size scale. So that's why quantum mechanics applies for electrons, and then, right, we're seeing kind of photons as well, since they're small packets. Okay, we kind of went through that chapter fairly quickly. So probably that'll be good because Thursday we can devote to math. The last little bit, since we have like 3 minutes, we can at least kind of quickly explain, right, how we know that light and electrons exhibit wavelength. And so going back, right, so now that we know that it's relevant on the de Broglie wavelength, so kind of, are we familiar with the double slit experiment? So the double slit experiment is again what gave them a bunch of evidence. So again, going back to what we expect if it behaved macroscopically, right? If you're trying to shoot electrons or light through 2 holes, if they were behaving like paintballs, right, we would expect them to just land directly behind and, you know, again, just kind of paintball splatter, right, directly on. But then what's kind of strange, and the significance of the double slit, is that it made a wave-like pattern, right? And I'll pull up the Wikipedia so we can look at the picture. But the key point is it made this repeating pattern, right? Not just directly behind it, again, if we were shooting a paintball, through this slit. So it was not only directly behind it, but again, here's a better actual picture, right? So you can see this laser pattern kind of repeating. So that's showing the wave pattern. And then what's also key is it creates this interference pattern. So again, you have these dark regions and then a node of no, nothing, and then a dark region and another node. So that's telling us, right, that again it's wave, since waves can kind of go around and bend around corners.
Didn't this experiment also have different results depending on if there was an observer or not?
I think it depended if they were perturbing it, was it? Because they would like maybe try to shine light at it, and that could, right, alter the signal. So I think that's might be what you're referring to, but. All right, yeah, we can end here now. So then Thursday, we'll focus on math, calculations, doing a lot of that. If you had other questions about like specific experiments too, we can also chat about that. But yeah, definitely, it's if you have like off-topic things, it's always helpful to like reference a paper or a certain experiment too, so we can like look at precisely what's going on. And then yeah, everything can just go. Yeah, just email the abstracts to me and I'll fix your grade too for the other one.
So I will be here on Thursday, but I'll go here first since we're traveling.
Yeah, I mean, you could come to lab today and maybe like just grab, because like I said, it's the cards. They're also online. So I think if you just go.
So we were like really close when I was like.
If you go to the lab page, and then there's these color cards or black and white cards. So like if you're not going to be here, I would print out those cards and you can do the lab at home. If you want me to print them, then come to lab and I'll print them out for you today.
Thank you. I'm gonna give this to you, but I forgot I don't have actually that. But I remember, I think I absolutely took this. I think I was supposed to do this.
Oh yeah.
Was I? Okay, I was like looking at why do I still have this? Was I supposed to write something at the top of my table?
Technically your table number, but it's okay. I already know where you sit, so it's fine.
Stuff sometimes. Okay, thank you.
Yeah.
I was gonna see if I could come to lab on Thursday. I was sick over the weekend and I'm still feeling out of it. So
Yeah, that's fine. Like especially for this week. Like I said, this one you could probably even like do at home. But if you do want to do it at home, just tell me so I'll be like, okay, you're doing it at home, and not I'm not just like what happened to Finn this week.
Okay, thank you.
Yeah, so just give me a heads up either way.
They were all the same.